Hey folks, a lot of things have changed from the last time I made the part one video of the talk we are doing. Uh, in this video, we'll see a general GPU architecture. We'll understand the execution flow of an instruction, how it's being given by the host CPU, and then how the computation actually happens. But before that, I'll show you my X account. So um, this is my X account. Wait, go check this out. I often shit post here. You'll enjoy it. Maybe you'll not, but go check it out. I don't have much to say about this. So let's get back to understanding the general GPU architecture. It has some abstraction units. Like the first one is this graphics processing cluster. So inside this cluster, you have some streaming multiprocessors. These are the major parallel processing executing units where most of the execution of the operation happens. Now this cluster contains this SM I told you about. It also contains raster engines. This we'll talk about later in this video, and it also has some other units like special function units. It also has tensor core units, RT core units. RT means ray tracing. We'll talk about this in this video. First, let's see what is an SM. Before that, I'll show you the Turing architecture of NVIDIA. This is the whole architecture, Turing architecture, Turing GPU architecture given by NVIDIA. So this this whole thing is one cluster, and inside this cluster you have some more units that are TPC. Inside this, this is whole GPC inside graphics processing cluster. Inside this you have raster engines, and then you have some abstraction units. Those are called TPC, that is texture processing units. Inside these units, all the calculation happens. Now inside this also, you have something called SM. SM is streaming multiprocessor. Okay, inside this, we'll see. Okay, this is one GPC. Likewise, you have a lot of, not lot of, but here for the Turing architecture, you have 6 GPCs. Each has 3, 3, 6. So we have in whole architecture, you have 6 GPC, and inside one GPC, you have one TPC, texture processing unit. So in all, you have 6 into 6, that is 36 total texture processing units. Now let's see one SM unit, that is streaming multiprocessor unit. So this is one streaming multiprocessor unit. It has integer 32 core, floating point 32 core, tensor cores. Then you have load store units and then special function units. So inside one SM, you have 4 processing blocks for this architecture, and in one processing block you have one register file, one warp scheduler plus dispatch unit. Then you have, I told you, you have int core, floating point core, tensor core, load store unit, and then SFU. Likewise, you have 4 processing unit per SM, and then you have one L1 cache, which is also shared memory. This is of 96 KB. It can be divided into 6432 or 3264 for L1 cache and then shared memory respectively. It also has some texture cores and then RT core for ray tracing. Now let's see in detail. So streaming multiprocessors are these are the main workhorses of the GPU. Each in each SM has CUDA cores. CUDA cores are basically those integer and floating point cores I talked about. These are basic ALUs. They perform all the arithmetic, logical, minimum, maximum, all the operations that are needed for mathematics. And then you have tensor cores. These are specialized cores for matrix multiplication and accumulate. So you have MAC, matrix, accumulate, So let's say for a tensor core, you get two 16 floating point values or operands, and then you get one 32 bit operand. So 16, those two 16 bit operands will get multiplied, and then it will be accumulated with a 32 bit this operand. So that's how multiplication and accumulate is done in tensor core. And then you have something that's called warp scheduler and instruction dispatch unit. What is warp? Warp is nothing but a group of threads. Usually it's 32. In the steering architecture also, it's 32 threads per warp. And warp executes the same instruction simultaneously on different data. So you have 32 threads that are working or that are executing same instruction but on different data. That's how it's single instruction, multi-thread or multi-data, multiple thread or multiple data. Now the dispatch unit receives the instruction from the warp scheduler. So the dispatch unit, and that's the dispatch unit gets the instructions from the warp scheduler, and it then decodes the execution, decodes the instruction, get the opcode, and directs the flow or directs the computation to the processing blocks. I mean, it directs the flow to the processing blocks where the main computation happens. So if the decoded opcode is, let's say, f add, which is floating point addition, so it will activate the processing block. Inside this processing block, it will activate the lanes of floating point operation, floating point core, and then the chosen instructions are dispatched to the available processing cores. You have register file. Basically, each thread have their own set of registers which are used for operations, and this is where these operands and intermediate results are stored. This works like L0 cache for the processing block. This is the now comes load store units. These units handle memory operations for the threads. It primarily manages global memory, but it also has access to L1 and some part of L2 cache. Special function units, these are used to accelerate complex mathematical functions like you have sine, cosine, logarithmic, square roots, etc. After special function units, you have texture units. These are used to apply texture to the 3D models. These are special hardware components that are used to apply texture after the sampling and filtering is done to the 3D model. Now you have RT cores, that is ray tracing. These accelerate ray tracing calculation. These have some specific functions to execute. So this specific hardware is to simulate the behavior of the light and then accordingly render the graphics. You have L1 cache that or shared memory. It's for this architecture. It's of 96 KB. I told you, kilobytes, and it's also shared memory for the data. So it depends on the programmer if he wants 64 KB for L1 cache and 32 KB for shared memory, or 32 KB for this L1 cache and 64 KB for shared memory. GPU employ a multi-level memory system to feed the data to the processing cores efficiently. So you have L1. Firstly, you have L0 cache, that is registers. These are very fast. These are local to a thread. And then you have L1 cache. It also has shared memory. These are shared within a SM, streaming multiprocessor. L2 cache shared. This memory shared across multiple SMs. And at the end, you have global memory that is accessible by all the threads. So since there is a memory hierarchy, So you need a memory controller. This will act as an interface between the internal memory of the GPU and between the internal GPU memory, that is where the processing units are there, that is where the calculation happens, and then and to the this external VRAM, which is global memory. Raster ranges, I told you, these are used to perform rasterization, and rasterization is basically the transformation of 3D models into 2D raster images. PCIe interface, this is used when you wanna like connect the host to the GPU. In our case, the host is CPU. NVIDIA also provides some interconnects, which are NVLinks. So if you want to connect multiple GPUs, then you can use this interconnect. Now let's see flow of execution. It's a coordinated effort between the CPU, that is your host, and the device, which is your GPU. CPU first prepares the data, that is your geometry, textures, compute data, and then it issues the commands to a GPU. CPU also defines a kernel function. The kernel function, like, it runs the GPU and it launches kernel. The CPU launches the kernel with specific grids and blocks. What is a grid? Grid refers to multiple blocks, that is overall structure of the parallel execution, and block is multiple threads. Multiple threads are also known as warp, but then a collection of warp is known as a block. So apparently you can say multiple thread means blocks. The GPU scheduler assigns blocks to SM. Okay. Now warp scheduling. What is warp scheduling? This block is assigned to a streaming multiprocessor, and then this block is split into warps. One warp typically has 32 threads. So the warp scheduler selects this threads which are ready to execute. Since it is a SIMT execution, that is single instruction multiple thread, so multiple threads executes the same instruction, but they execute the same instruction on multiple data. That's how this multi-threading works. Same instruction but on multiple data using threads. Memory access. This memory access happens through load store units. Synchronization. Threads inside a block can synchronize. This sharing of data happens through shared memory, which was of either 32 KB or 64 KB based on the programmer, and then this will synchronize the threads. But then if the threads are located in different blocks, they can't synchronize directly. For that, you'll have to close the kernel and then relaunch a new kernel. After the warps and blocks have executed, the result is stored back in the GPU, and CPU then uses this result to access or to launch a new kernel function. See, building projects is like, especially building projects with minimal knowledge you have about the subject, is sometimes hectic, but it's so rewarding at times, because you learn a lot of things in a small span of time, and you practically implement that thing on the very same time. So it's been this strategy is so helpful for people like me who want to explore a lot of things but don't want to get into things more deeply. I just want to explore multiple things and then later on choose a specific thing which I like and then advance in that on that field. So that's it from this video.
Want to be the greatest. Everybody on the fake shit. I look around and feel like everybody is the fakest. I make this every day and I'm impatient, hoping one day I blow up from the basement. Statement, the top is so vacant. I don't hear shit that I think is amazing. Waiting for my day when I'm playing sold out shows for 1,000